Hello everyone, welcome to Mindspan Education. In this video we are going to look at the central limit theorem. Central limit theorem tells us that the sum of many independent identically distributed random variable has approximately a normal distribution. If you recall from one of our videos where we were discussing about sum of two random variables, right? So we have already seen that, let's suppose if we have this random variable x1 and it has the distribution that is uniformly distributed from 0 to 1, and we have another random variable x2 and it has the same shape or the same distribution as x1. So this random variable x1 is also uniformly distributed from 0 to 1, right? And if you try to find the overall distribution of the sum of these two random variable, then what we do, we convolve this PDF, and ultimately we have seen the convolution of these two rectangular PDF, or the distribution of the x1 plus x2, that is the sum of these two random variable, will have a shape of a triangular type, right? This we have already seen. So here if you see, we have just taken two random variable, right? And both of these random variables are independent and both have the identical distribution, and we are trying to find what will be the distribution of the sum will look like, and the distribution of sum is of kind of a triangular shape. Now you can imagine this is just we have done for n is equals to 2. So we have just taken two such distribution, two such identically independent distribution. Let's suppose if we take 3, 4, 5, 6 such identically independent distribution, then this shape will tend to take, or this shape of the sum of those identically independent distribution will tend to take the shape of the normal distribution. So this is what the central limit theorem is saying, that if you have the independent identical distribution and if you do the sum of those IIDs, that is the independent identical distribution, the distribution of this sum will approximate to the normal distribution, right? And why it is useful? Because for the normal distribution we have the CDF that is in the table form, right? So we know the probabilities, or we know the calculation that how to deal or how to find the probability in case of a normal distribution. If we know this, and if you know that the sum is converging to the normal distribution, that means we will be also able to find the probabilities of these sum of the random variables, right? And here I have taken the distribution, the identical distribution of uniform random variable, right? So the distribution is uniformly distributed, right? But this statement, the central limit theorem, is true for any kind of distribution. So maybe you can take the distribution of this random variable x1 that will look like this. Let's suppose it is defined from the x1 is defined from 0 to 1. It is taking the value from 0 to -1 to 1. So take such an identical distribution and add up, right? So ultimately this distribution will converge to, or will take the shape of normal distribution, right? It doesn't matter what kind of distribution that these random variables have, right? And obviously all what we are talking is that all will have the identical distribution. So you can take any shape of distribution, and if you add such n distribution, so the sum of the distribution will have the distribution that will look like normal distribution, right? Again, it depends upon the shape and how many such distribution you are adding, right? So if you take the normal distribution x1 as a normal distribution itself, right? So you just need n is equals to 1 such that will be equal to the normal distribution, right? And let's suppose if you are taking the x1 as this kind of distribution, then for addition of these distribution, these such two distribution, you have the shape of this triangular shape, right? So maybe for n is equals to 32 or maybe 30, the distribution will tend to look like a normal distribution. So depending upon the shape and depending upon this n, that how many such distribution I need so that it tends to look like a normal distribution, right? But the ultimate result is that as you increase the value of n, right, for any generic distribution, identical distribution which have a defined mean and variance, if you try to find the sum of the distribution, then the sum of the distribution will approximate to the normal distribution. Now let's try to look at the distribution of the sum of these independent identically distribution. So we are going to see that. So let me first of all tell you that let's suppose if we have these random variables x1, x2 and xn, these are independent and they have identical distribution. And let's suppose since they have the identical distribution, we can just talk about one distribution and it has the mean mu and variance sigma square. So each of these random variable are independent and it has the mean mu and variance sigma square. Similarly, it will have the same distribution with the same mean and same variance, and for all these random variable, right? And now let's try to look at the distribution of the sum. So let's denote this sum as Sn. So sum of these random variable, that will be x1 plus x2 till xn. Let's try to have a sense that if we try to increase the value of n, what kind of distribution we will be getting. Let's try to have a sense on that first. So if we try to find, or if I ask you what will be the variance of this random variable Sn, you can easily find, since these random variables are independent and each have the variance sigma square. So since these are independent, the variance of this random variable will be the sum of individual variance, right? And we have such n terms, each have the variance sigma square. So the variance of this random variable Sn would be sigma times n times sigma square. Now if you try to increase the value of n here, the variance of this Sn will tend to also infinity. And what does it mean that variance is infinity? What is variance? So variance gives you the information about the spreadness, that how the distribution is spread out over the real line, right? So if variance is higher, that means the distribution will be more spread out, and if variance is low, the distribution will be narrower, right? So if variance tends to infinity, what does it mean? It means that the distribution will be spread out throughout this real line. So the distribution will tend to take a larger value, and so overall we will have this kind of distribution that will be kind of flat distribution, right? So here no point of convergence that we see, right? If we are increasing the n, we see that it doesn't converge, right? As per the central limit theorem, this should have, or this, the distribution of this Sn should converge to something that have approximately like normal distribution. But if you see, what if we are trying to increase the value of n, then the distribution is getting more spread out, and ultimately the distribution will be spread out throughout this real line, and you will have some constant distribution, right? So again, this is not converging as expected. Next attempt, what we can do, let's suppose that we divide or scale this sum of these IIDs by n. In this case, if we try to look at the variance of this random variable Sn when we have scaled by n, then in our, what will be the variance of this random variable? Since we have scaled, we know that the variance of this random variable x is sigma square, then the variance of this random variable x divided by a will be 1 square times sigma square, right? Then the variance of this random variable will be n times sigma square divided by n square. So overall we will have sigma square divided by n. Now if we try to look at as we increase the n, then the variance of this random variable Sn will be 0, right? Now if you try to look at the distribution, so for a very large n, right, so this distribution will be concentrated around a single point, right? Because you have the variance that is 0, that means there would be no spreadness in the distribution, so the whole distribution will be concentrated about this small, very small region, right? So again, there is no point that we see that this, as we increasing n, then we do not see that it is converging to some normal distribution, right? What further attempt we can do, let's, instead of dividing by n, let's divide this sum by root n. In that case, we will have the variance of this random variable Sn, that is n sigma square divided by root over n ka square, that will be n, and we will have the variance that will be sigma square, right? Now we have achieved something, that if you are trying to increase the n, the width of the distribution remain constant, right? And instead of dividing this by root n, let's divide it by root n times sigma, right? So that we will have overall the variance that is 1, right? Now if you try to increase the n, we will have the distribution that will have the fixed width, right? But there is one problem, there is one more problem, is that if these identical distribution have non-zero mean, then if you try to increase the n, then every time the mean will get shifted. As you increase the n, the mean will not be fixed, it will get shifted. Why? What will be the mean of this random variable? The mean of this random variable will be n times how many such random variable we have, n, and each have the mean mu, right? And if the mean is non-zero, it depends on the value of n. Now let's come to this. So if, what will be the mean of this? So mean of this will be so it will be again depending upon n, right? Because root over n times n into mu, right? So overall you will have the root over n times mu. So as you change the value of n, every time you will have a distribution that will have the different mean. Again, it is not converging, right? There is no point of convergence, because since we are changing the n, the distribution will have different mean as per the value of n. So there is no point of the convergence. So what we can do, first we can shift this distribution to its mean, right? So what we can do, first we can make the mean of this distribution to 0. So in order to do that, we can simply shift this to the mean amount. So mean of this random variable is n times mean of individual random variable, right? So once we have shifted this distribution to this amount, now this will have the mean 0, right? Now once we have done that, then what we can do, we can scale this by quantity, so by root over n times sigma, right? Now we can say that we can give this new quantity as a new random variable, that let's call this as a Zn. Now if I ask you what will be the expectation of this random variable Zn, that will be 0. What will be the variance of this random variable Zn? That will be 1, right? And it will be independent of this n. The mean will be always 0 for this random variable Zn. The mean will be always 0 and the variance would be always 1 irrespective of the value of n, right? Now if we increase the n, right, if we change the n, so we have the expected value and the variance that is independent of this n, but the distribution is depending on this n, right? So distribution will be changing, but the mean and the variance will be fixed, right? So we might guess that now this distribution may tend to converge to normal distribution. So the distribution of this random variable is changing as we are changing the value of n, right? So overall point is that this is what central limit theorem says, that now this distribution will have the as we increase the n, the distribution of this Zn will tend to take the shape of normal distribution, and this is what the central limit theorem says, right? So this distribution converges to the normal distribution as we increase the n, right? So this central limit theorem states that as n goes to infinity, the distribution of this random variable converges to a standard normal random variable. So the same thing we can say in the probability sense, that the random variable Zn takes the value less than equals to little z. The probability of this is approximately same as the probability that this standard random variable z takes the value less than equals to little z, right? So this probability as n goes to infinity, or as we increase the value of n, this probability that is the probability of this random variable taking the value less than equals to little z is same as finding the probability of the standard random variable taking the value z is equals to little z. And the very good thing is that we have the table for this probability, right? This is the calculation of the probability of the standard normal random variable, right? And we have the tabulated form of the CDF of this random variable, of this standard random variable. So in order to find this probability, right, we can simply look at the table and we can find the probability of these Zn. All right. And you might be curious about the proof of this central limit theorem. So the proof that the proof is not as simple as that. It involves other mathematical concept. So we are not going to look at the proof of this central limit theorem. Right, so we are just going to look at what is central limit theorem and problems based on the central limit theorem. That is it. Right. So now here what we can say is that here we have just the CDF of this random variable. So what is this? This is nothing but the CDF of this random variable Zn. So it tells us that the CDF of the random variable Zn converges to the CDF of the standard normal random variable, right? And I have already mentioned that we can find the probability of this standard random variable just by looking at the standard normal table, and once we have that value, then we will also have the values of calculation of this probability. We will look at few more points regarding this central limit theorem, and we will be looking at the problems in next video. That is all in this video. Thank you so much.